Hi, everyone. So today we're very happy to have Jon Sorce visiting us from MIT. He did his PhD with Patrick Hayden at Stanford. Then he moved to MIT and he's been there for 3 years. And I just learned that he's moving to Princeton in a couple of months, I imagine. Yeah, he'll be talking about gravitational constraints, modular flows, and something I can now read from here.
Info theory of UV divergence.
Thank you.
Okay, thanks, Nima. So great to be here. Like Nima said, I'm a postdoc at MIT. I work on the information theory of continuum systems. So things like entanglement in quantum field theory, connections to quantum gravity, and how you can probe all of these things using theory. So this can be a rather technical subject, and I don't want to lose people. I want this to be a very accessible talk. So what I've decided to do is spend most of my time today talking about motivation, big picture questions and considerations, and maybe spend the last 15 to 20 minutes of the talk summarizing the actual results from this paper that I'm focusing on today. So this is work in progress with Gautam Satychandran, and the point of it is trying to ask essentially, how much is universal in quantum field theory in the information theoretic sense? What is sort of the universal content of quantum field theory that can be probed by information theory? And the rough outline of the talk is I'm going to start by talking about this technical tool called modular theory, which is the chief mathematical tool that is used to describe information theory and continuum systems. Then I'll talk about some core ideas about information theory and continuum systems and how they relate to semi-classical quantum gravity. And then finally, I'll tell you a bit about how we're investigating these in free field theory. People are often surprised to learn that we're studying things in free field theory. It turns out that if you ask questions about the S matrix, free field theory is totally trivial. But if you ask questions about entanglement, it's actually an extremely subtle theory and something that has a lot of content to it. Okay, so to start, let me talk about the tools that I can use to talk about information theory and continuum systems. But maybe to orient everyone, I'll first tell you about the tools we use to talk about information theory and discrete systems. So first, maybe let me say, quantum information theory is the statistical analysis of subsystems. That's all it is. It's quantum theory applied to subsystems of a larger system, and then studying those subsystems statistically. So what you typically do in order to do quantum information theory is say you take some global system, say consisting of a finite number of lattice sites, and you divide it into two complementary subsystems, R and L. And the way that you describe this mathematically is by taking your global Hilbert space and factorizing it into two tensor factors. And then what you do if you want to describe, say, the physics going on in subsystem R, is you take some global pure state on R prime, you trace out the R prime system, and you end up with the density matrix, which is an operator acting on the tensor factor corresponding to a particular subsystem. And all of quantum information theory is in studying the physics of this operator, or rather studying the physics of this subsystem through the mathematics of this operator. When you try to apply similar considerations to the continuum, there are serious issues. So what do I mean by a continuum system? Say, for example, I mean a quantum field theory. And if I want to divide the degrees of freedom of my quantum field theory into two complementary sets, the way I do that is by drawing some space-time diagram in which I single out some causal region, R, where certain degrees of freedom live, and a complementary causal region R prime, where the complementary degrees of freedom live. And there's a problem in quantum field theory, which is that there's an enormous, in fact, divergent amount of entanglement between these two systems due to the buildup of ultraviolet entanglement at the edge where these two regions touch. And what that means is that the global Hilbert space of quantum field theory does not tensor factorize. Instead, you need some new kind of structure to talk about the division of the degrees of freedom into R and R prime. Maybe one thing I should say is that, as is typically the case, one can restore this factorization by putting in a regulator, and that's useful for a lot of things, but for the things that we're going to talk about today, the regulator actually obscures the physics, and so it's useful to talk just about the continuum system on its own footing. So instead, what you have are operators that live in R and operators that live in R prime, and together those generate all of the operators of the theory. It's like the Heisenberg version of this picture. So the way we write this is as following. So we say the full set of linear operators acting on Hilbert space can be generated by, this is some symbol that I haven't told you what it means for generation in the algebraic sense, operators living in R and operators living in R. Okay.
And if you have one right in the intersection,
So there are no operators in the theory that live right at the intersection. This is a subtle point. You can put fields there, but operators in field theory need to be smeared slightly to get rid of divergences, and that stops you from actually putting operators right at the intersection. Or if you like, you could say if you were to allow operators that were right at the intersection, then maybe you would put them in both. They would still generate everything. So when we do continuum information theory, this thing that we started with on the lattice, which was a Hilbert space tensor factor, gets replaced by an algebra of operators. And then there's a question, which is what happens to the density? What is the thing that we have available to us in the continuum to do the same thing we could do on the lattice using density matrices? Well, let's first give a proper definition of a density matrix. So given a global state psi and an algebra describing a subsystem, we say that a density matrix is an operator in the algebra that has all positive eigenvalues and that gives all of the expectation values via the standard formula for density matrices. This is also how the partial trace here is defined. This is how this rho R is defined on the lattice. I guess maybe I should put a subscript R to make all of this. Okay. So there's a problem with trying to just take this definition and apply it. Which is that in QFT, it may be the case that no such thing exists. Okay. This typically happens in QFT. I won't give you a proof of this, although it's been, discussed in many contexts. In QFT, typically, all of these operators have infinite trace. And this comes from a UV divergence. Basically, if you were to put your quantum field theory on a lattice and you were to try to write down something that would play the role of the density matrix, you would find that it had an arbitrarily large support on these UV modes here that would cause a divergence when you went to the continuum. So there's a fix-up, which is very commonly used by people like me and Nima, which is to say, well, okay, this density matrix just doesn't exist in the continuum. It has a UV divergence. Is there anything that subtracts off or divides out by that divergence that we can use instead? And indeed, what we typically do is instead we look at this combination of density matrices. And we call it delta. So we say, take the density matrix of the system you want to study, and then tensor in the inverse of the density matrix on the other system, with the idea that if the divergences are multiplicative, then these things will cancel. this object is called the modular operator. And while the definition I just gave you is one that uses a fundamental lattice description, there is an intrinsic continuum description that I won't talk about during this talk. But there's a way to define this purely in the continuum using what's called modular theory. And it makes no reference to the ideas of density matrices or lattice regularizations. Okay. So when people like me try to study information theory in the continuum, what we do are we study the properties of these operators. We look at quantum field theory states, we divide them up into subregions, into subsystems, and then we try to understand what are the properties of this operator. How can we use that to extract information about the entanglement, say, between this region R and the complementary region? There's a very natural thing to do, which is this thing is a positive operator, which means that minus the log is Hermitian. If you take something that has all positive eigenvalues and you take the logarithm, you're going to end up with something with all real eigenvalues. And what that means is that when you want to study this delta, you could equivalently study the log of delta. And trying to study a Hermitian operator is something that we're very used to from the perspective of quantum mechanics, of trying to study a Hamiltonian describing a quantum system, trying to understand, say, its spectrum and its eigenstates. And one thing we often do when we're trying to understand the Hamiltonian of a quantum system is look at the time evolution it generates. So it can be useful in our goal of understanding delta to study an associated evolution map, which takes operators and conjugates them by a time evolution with big scare quotes around it. Generated by this operator. And this is called modular flow. So these are two perspectives that people go back and forth between very quickly when they're studying this subject, is studying this operator directly or studying the flow that it generates. Tell you one more thing about this flow, and then maybe we'll pause to take stock before going into the second part of the talk, which is that the key tool that we have for studying this is to study how it acts in correlation functions. So for example, we might look at a modular flowed correlation function, FABS equals psi. I'm going to stop writing this as a logarithm and just write it as follows. Okay. We might study this correlation function, and actually the strongest control we have over this correlation function comes in the form of its analytic structure. There's something called the KMS condition. This is often rather difficult for people to process, so I'm going to pause and try to explain it very thoroughly. The KMS condition is that if you take this correlation function, you do some of this funny time evolution, and then you do an analytic continuation, you end up switching the order of the operators in the correlator. Now, this is something that people maybe haven't seen before, but it's extremely typical as a feature of thermal physics. In fact, KMS stands for Kubo, Martin, and Schwinger, and these people originally studied this in the context of thermal field theory. So maybe let me make some comments. One thing that we often say about thermal systems is that they have some periodicity in imaginary time, right? Thermal systems are sort of generated by doing some amount of finite Euclidean time evolution, and that introduces some essential periodicity in thermal time. This condition, if I had taken this to be the time evolution generated by the ordinary Hamiltonian, would be exactly the statement that the theory has some fundamental periodicity in Euclidean time. I would say, look at the time-evolved correlators, do some analytic continuation in Euclidean time, and you end up with some kind of periodicity condition where the order of the operators is switched. It tells us that a generic state, when examined relative to its modular Hamiltonian, its modular flow, looks like a thermal state when examined with respect to ordinary time evolution. The reason I'm bringing this up is because it is an extremely useful condition for studying and identifying these modular operators. In fact, I was just talking with Nemo over lunch about this. Which is the fact that given a state in an algebra, the modular operator is the unique operator satisfying KMS. And what that means is that if you're trying to study the density matrices of some continuum quantum field theory state, and you're trying to study the entanglement structure, what you can do is you can look at the analytic structure of the correlation functions, try to identify some flow that satisfies this condition, and then use that to deduce the form of the modular operator, which actually encodes the information theoretic properties of your state. Okay, that is all of the mathematical technology that's going to be used in this talk, but maybe I should pause and ask if there's any questions, because, you know, this is math physics and maybe takes a little bit of time to process.
I mean, those seem to emphasize the states that have a eigenvalue close to 1 instead of 0, for example, but why don't you do this in Minkowski? Why do you put the I there?
Sorry, say that again.
Suppose a density matrix would have eigenvalue 0 or 1, let's say. So if it's 0, you get minus infinity, so you get minus log is infinity. And if you have 1, it's 0, so.
Well, a density matrix typically has a range of eigenvalues between 0 and 1.
Yes, so the ones that this would emphasize more. So the log delta will be very large for the ones that are close to 0, and will be very small for the ones that are close to 1.
That's right. That's right.
So if I were to do Euclidean evolution, I will keep the most representative state with the flows. But if you do with I, you can make them oscillate.
Yeah.
What are you doing exactly with this flow?
Well, it's like the same thing is true of ordinary time evolution in a quantum system.
Yes,
Right, is
yes.
that the phases of the high energy states oscillate very rapidly and the phases of the low energy states oscillate very slowly.
But that's just what evolution is. So I don't have any choice, but here that's not really, you are just doing it for some purpose, I guess.
Yeah, well, that's true. I mean, maybe another thing to say is that this is a trick for studying a state. And it's sort of the thing that looks most like studying a thermal state by looking at time evolution. It says make up some funny time evolution so that your state looks thermal, and then you can apply thermal principles. So it's kind of like if you study ordinary thermal physics, you start with a Hamiltonian and you turn it into a density matrix that looks like this, right? But in modular theory, you go the other way around. You start with a density matrix and you rewrite it as e to the minus log rho. And you call this H. But it's just a trick. It's just a way of saying I'm going to take a generic state and I'm going to try to study it using the same principles I use in ordinary statistical mechanics. Any other questions? Okay. So now let me talk a little bit about an interesting feature that one would like to study in quantum field theory using this technology, and how it actually has an interesting connection to quantum gravity. So I've told you what this generic framework is. Let me tell you a little bit about the most famous example in which this framework is applied. So by people in sort of a specialized community, this is called the Visignano-Wickman theorem. But to a broader audience of physicists, this is what is known as the Unruh effect. So I've told you that we have some technology for studying quantum fields in some state in some subregion. So let's think about the simplest example. Well, our simplest example of a subregion is going to be taking Minkowski spacetime and dividing it into two half spaces, the Rindler wedge R and the complementary Rindler wedge R prime. And our simplest possible state is going to be the global Minkowski vacuum. So the fact, which was studied by Unruh in free theories and studied by Visignano-Wickman in general theories satisfying the Whiteman axioms, is that if you compute the modular operator of the vacuum in this Rindler wedge, so if you try to understand what the density matrix looks like in this Rindler wedge, what you find is e to the minus 2 pi times the generator of boosts. Okay. So all of this stuff I said about the KMS condition and the connection to thermal physics is said heuristically as omega is thermal with respect to boosts with inverse temperature 2 pi. Okay. The modular flow looks like this. This is a famous statement in quantum field theory. It's the same statement as the statement that a uniformly accelerating observer, someone following a boost trajectory, will experience the vacuum as a thermal bath. So now I want to take this observation and connect it with a piece of lore in quantum field theory. So the lore is a rather imprecise statement, as all lore is. The lore is that every good QFT state looks like the vacuum, what looks like in quotes, at short distances. So this is an imprecise statement that can be made precise in many ways, but it's sort of an intuitive statement about quantum field theory. It's the statement that if you're studying a quantum field theory and you're studying some state of physical interest, then typically this means it has some finite energy excitation above the vacuum. And if you zoom into short enough distances, all of the scales that you've put into the state should wash away and your state should start looking like the vacuum. So there are sort of two things that need to be made precise in this statement. Good needs to be made precise. Is this supposed to apply to all quantum field theory states or just the ones that show up in experiment? It's something that you need to be careful about. And then you also need to decide what you mean by looks like the vacuum at short distances, right? Looks like is a very, very imprecise statement, something that sort of begs to be made into an equation. Now, there are many ways of formulating this, but a common one that is sort of an old conjecture in my community comes from taking this lore and relating it to this observation. So the vacuum density matrix looks like the thing that generates boosts in quantum field theory. So then the question is, does every quantum field theory state somehow reproduce that behavior deep in the UV? So the conjecture, which still is imprecise, is every good QFT state psi is boost-like. Oh, sorry. Every good QFT modular flow is boost-like near the edge. So the idea is that if you have a generic quantum field theory state and you restrict it to a region and you try to study its entanglement properties by looking at the modular flow, well, it might look totally crazy in the interior of the region, but near the edge where ultraviolet effects dominate, you might expect that this starts to look. This is a deep statement. It's something that sort of is getting at the idea that entanglement in quantum field theory is universal at very, very short distances.
Question?
Yeah.
If you are in theories where you could make sense of operators living null separated from the edge, living on the horizon, doesn't that we wouldn't expect the behavior of that to be boost, right? In a generic state, because that would say that
Not here. But here, yes.
the proper distance is 0.
Yeah, but the edge is characterized by, the edge is more special than just proper distance 0 from
So,
the
but
edge.
then the word near needs to be made very sharp, because there's
I
no
agree.
sense of this point being nearer
I agree.
0 proper distance away.
Yeah, but because this is supposed to be an asymptotic statement, as you zoom in on the edge, as you take arbitrarily small open sets of the edge, those start cutting out
I
this.
guess I'm asking, is there a covariant way of describing that?
Possibly not, but the example I'm going to talk about today involves everything localized on the null surface, so there it will be clear.
So you're gonna have an affine parameter or
Yeah,
small.
yeah, that's exactly.
That's a trick that, yeah, it's a good trick.
Yeah,
It's not-
yeah.
that's related to
It's a trick that
self-help.
works in the example I'm
Yeah.
talking about.
Yeah.
Okay. All right. So there's one thing I want to tell you before, so I've set up this question. I think it's an interesting one just about sort of the entanglement structure of quantum field theory. But I want to tell you the reason that I actually started thinking about it, which is not going to be the subject of the rest of the talk, but I think it's sort of good to have in the back of your head, which is that there's an extremely deep connection between this conjecture and quantum gravity. And I'll just sketch this. This is an idea that's been around for some time. So when you study quantum gravity, you do many things, some of them better justified than others. But one thing that is extremely well understood is that in quantum gravity, black holes carry an entropy. And the entropy that they carry, called the generalized entropy, is proportional to the horizon area of the black hole divided by a Planck area, plus the entropy of matter fields that live outside the black hole. And there's a problem with this formula as it's written down, which is that both of these terms are infinite in the classical limit. So the classical limit, the thing that we see in our universe, is where gravity is very, very weakly coupled. And in that limit, this term diverges because G Newton goes to 0. And this term diverges because of UV divergences involved in the entropy of matter in quantum field theory. There's an old idea, sometimes attributed to a lot of people, Sorkin, Solodukin, Susskind, and Buckland, among others, which is that perhaps these two divergences are really one and the same. And perhaps this combined quantity is a real physical quantity that is UV finite.
So, good question.
Yeah.
There are divergences even when G Newton, both term are show divergences even when G Newton is finite. in
Yeah,
the
because
sense
of you're saying
RG.
the one loop renormalization of G Newton?
Yeah.
Yeah, that's just takes longer to explain.
Yeah.
Yeah. But yeah, indeed, if you try to just treat this as a field theory, then this ends up, if you try to treat gravity as a field theory, then this is a bare parameter that ends up being infinite and has to be renormalized. And that's the divergence that Newton's talking about. Although the sense in which, that's like a perturbation theory calculation, so the sense in which G Newton is finite is like a little subtle. It's finite and
That's what
small.
we're normal, yeah.
Yeah, yeah. It's a problem in doing perturbation theory, let's say. Okay, but let me connect this lore. So we have 3 pieces of lore so far, right? Let me try to connect this one to this one. So a fact that's been known for a while is something that happens when you try to canonically quantize quantum gravity. These 2 things get connected. So how does that work? Well, the first thing to notice is that in quantum gravity, the area of a black hole horizon is an observable. Right? If I let the space-time fluctuate, then the area of the horizon is also going to fluctuate. So it's something that depends on the wave function of the universe, depends on the wave function of the black hole. It's an observable quantity. So if you think about some phase space picture of quantum gravity, you can compute Poisson brackets of this area observable with other gravitational observables. And what you find is that this Poisson bracket, if this is the place where A lives, this is the horizon of the black hole, what this Poisson bracket does is it essentially generates a discontinuous boost. At least locally. Kind of does nothing on this side, and then it introduces a little bit of a kinked sort of discontinuous boost on this side in the exterior of the black hole. This introduces divergences, right? It takes some sort of smooth data for Einstein's equations and it introduces some infinities into it by creating this divergence in the initial data, this discontinuity in the initial data. But roughly speaking, area plus a density matrix is well behaved if rho r to the minus is looks like a boost. That's sort of the point, is that these area operators generically introduce some kind of discontinuous
You mean
boost.
log of rho?
Thank you. And maybe I mean a minus.
Yeah, no.
I probably mean a minus. Yeah. Okay, but I won't commit to sign right now. Okay. But the idea here is that this discontinuity, which appears universally in quantum gravity when studying black holes, seems to have exactly the right form to be canceled by this conjectured universal form, universal ultraviolet form of the modular flow or the density matrix in quantum field theory. So this is one reason, I'm not going to talk about this at all in the rest of the talk, but just to say that one reason that we really want to understand this is because we're trying to understand the entropy of black holes in quantum gravity and how all of these infinities can be made to go away if you're careful about the theory. Okay. That is it for the second part of the talk. In the next part of the talk, I will tell you what we did in free field theory. Any questions about Poisson so far?
In making this connection, do you need to restrict the bipartite filling horizons?
I was in my head, really it would be fine to just have an extremal surface. So this Poisson bracket works for any extremal surface.
Extremal surface, okay,
Yeah.
that's right.
Yeah, so this was computed by, okay, Busso, Rath,
Yeah.
maybe Shabazzi Magadon. You know the paper I'm talking about? It's called like the gravity dual of Kahn co-cycle flow.
I don't know the problems with that paper, but anyway.
Well, the problem is that it doesn't have anything to do with Kahn co-cycle flow.
It has nothing to do with
But Pratik actually told me recently that he thinks the paper should have been called the kink transform. Which
It
is,
is an interesting transformation, but it's not.
yeah,
common.
no, I agree, but whatever, that's fine. Okay. Okay, so I've told you a conjecture. I've told you why I'm interested in it. I'm not going to totally resolve the conjecture, but I'm going to give you evidence for it, at least in an example where I know how to compute things. And that's the new stuff in this talk. So I'm going to go to a theory that is totally mathematically well defined, where I know how to compute everything, at least in principle. And I'm going to try to compute. So I'm going to consider a causal diamond, D, in Minkowski spacetime. And I'm going to ask, is boost universality enforced in D? Okay. Now, concretely, what I'm going to do is I'm going to construct for you a bunch of states that look like they have some modular flow, some well-controlled modular flow behavior near the edge. And then I'm going to show you that those states are pathological if the edge behavior is not boosted.
Massive scalar,
I'm going to choose the massless scalar.
massless scalar, so CF.
Yeah, I'm going to choose the massless scalar. I think it doesn't super matter because I'm showing necessary conditions. I'm ruling things out, and they'll also be ruled out in the massive scalar too. But it's a little subtle.
But in the math, in the CFT, you do have, oh, for arbitrary region, okay, yeah.
No, I'm still talking about a causal diamond, but I'm going to be looking at different flows than the one that you're thinking of.
Okay.
I'll write down an equation, I think, in a moment that will make this
Sure,
clear.
sounds good.
Okay. So concretely, I'll pick a vector field on what's called the path null boundary of the diamond. So this is a diamond. It has some, dimensions going in and out of the board as well. Its past null boundary is some cone. Okay? And this cone has an affine direction, u, which goes in a null direction along the cone, and it also has an angular direction, omega. And what I'll do is I'll pick some vector field that points along the cone. And I'm going to try to ask, could that vector field be realized as a modular flow? So I'm going to call this vector field x of u, comma omega, d by du. So it points in the u direction and it has some profile.
It's arbitrary vector field. It should vanish at u equals 0.
It's going to need to vanish at u equals 0 and at u equals 1.
And x is always positive.
X is always positive. Yeah.
That's good. Okay. The vanish of the those two points and it's always positive.
And actually that's kind of not enough. You also need it to vanish slowly enough at the tip and the edge that it is
Sure.
integrable as a transformation. But okay. But we're getting a little ahead of ourselves. So what we're going to do is I'm going to construct a set of correlation functions. Labeled by this vector field. And I'm going to choose these correlation functions such that they satisfy this KMS property with respect to the flow generated by this vector field.
Sorry, don't you need the first term expanding x in terms of u? Don't you need the first term to be u?
That's what it's gonna, that's the whole point. The whole point is that we're gonna show why that has to be the case.
And then at the second order, anything goes and you're fine.
Second order has to be like a power. U log u is bad, but u to the 1.2
Oh, it's
is fine.
analytic.
It doesn't even need to be analytic. U to the 1.2 is okay.
Oh,
Yeah. It needs to be at least as slow as u to the 1 plus epsilon. But we're getting ahead of ourselves. Okay. So the goal, which Nima just anticipated, is I'm going to construct these states. And remember, this KMS property uniquely, it's an analytic thing that uniquely characterizes modular flow. So I'm going to ask when these correlation functions can be realized by some vector in the vacuum Hilbert space. And I'm going to tell you that this can only happen if x goes like 2 pi u, 2 pi 1 minus u at u equals 0 and u equals 1. So this is what Nima was anticipating.
So, sorry, these points are all on the cone. They're limited to the cone, right? Otherwise, they're not.
No.
No?
I'll tell you in a second. This is going to be a full set of correlation functions.
In the ball.
We're in anywhere in this diamond.
Oh, wow.
Okay. I'm going to specify them using the equations of motion just by telling you what they do on the cone. But I'm going to use the equations of
sure.
motion to get from there to the full bulk of the cone, the bulk of the diamond.
That's where the non-locality comes out.
I'm going to construct these so that they have the KMS property with respect to my chosen flow. But then I'm going to tell you, well, it looks like all of these are perfectly good sets of correlation functions, but not actually all of them can be realized as quantum field theory states, as real preparable states that you can get from the vacuum. And the condition we're going to find is exactly that we need to have this boost-like behavior. So this is the claim, and it's something that we've proved, and I will summarize the proof for you. But the point of this, this is the punchline. The punchline is that we really can show that this conjectured universal behavior is enforced within this special class of examples.
Sorry, the claim is for arbitrary space-time dimension and
Arbitrary
mass,
space-time dimension,
Massive
mass equals 0.
Mass equals 0.
Yeah, I don't think that's space-time dimension bigger than 2, mass equals 0. Space-time dimension equals 2 is fine. It's just that then you need to take a compact boson instead of a, this isn't very deep.
Yeah, the massive case is the worst. Would be fascinating.
The massive case is not that much harder to treat. It's just you don't have any conformal tools to use. But let me tell you exactly how we're going to do this. So there's a fact which uses the equations of motion of theory, which is that if you have any point in this diamond, you can take the field localized at that point, and you can rewrite it in terms of data that's just on this cone, right? Because the free field has a simple equation of motion. It's a PDE that has initial data down here. And the formula, I'll write it for completeness. I wasn't careful about signs or prefactors in my notes, so I'm gonna write a little tilde there. This looks like an imposing equation, but it's really pretty simple. It says, take the field, restrict it to the cone, apply some differential operator to it, and then integrate it against some kernel. So this E is a Green's function for the Klein-Gordon equation. It's a particular Green's function for the Klein-Gordon equation, and it gets you back this field here. So it essentially says, if you have some phi x up here, then it can be represented as an integral over this sort of time-like separated points on the cone. And this is where this kernel E lives. Okay. So the reason we do this is because it means that we can specify arbitrary correlation functions effects just by specifying what the correlation functions look like for fields localized to the cone.
So there's something that confuses me. If you are in massless free fields, the boundary of that E should suffice. Why do you need to even be inside that E? If you have a massive
What you
field.
said is correct in even dimensions,
Oh, I see.
but I'm
So
being
in
very
odd,
general.
2 + 1 is not true.
Yeah, in odd dimensions, the massless propagator does go inside the light cone.
Oh.
Where does that middle term come from?
It comes from basically what you do is you take this thing. So you take 5x. And you write it as a space-time integral of phi y against delta y minus x. Right? And then you write this thing in terms of a Green's function. So this looks like box E, right? The delta function is the derivative of a Green's function. And then when you integrate by parts, you move derivatives over to phi. And you have two derivatives here. One of those derivatives turns into the divergence that gives you a boundary term, but the other one is left over in the equation and it takes this form on the cone. Incidentally, I certainly could have just absorbed this into E, but then E wouldn't have been the Green's function for the, for the Klein-Gordon equation. Nima, if you want to work just in even dimensions, could have drawn a different picture, but this is the most general case.
Yeah, no, that's very good. That's very good. It's just a subtlety I had not realized.
Yeah. I actually, briefly, when I was writing the draft, I considered restricting to 4 dimensions because I didn't want to deal with this, but you know, it doesn't really change the story. It doesn't change the story because this factor of U suppresses everything near the tip of the cone so much that having support all the way down to the tip of the cone doesn't change things.
Also, you're working explicitly, you know those functions. It's all.
Yeah,
it's like
exactly,
conformal
exactly.
symmetry.
Yeah. That's
Yeah.
right. Okay, so let me say a fact that we're going to use as inspiration. Or 2 facts. The first one is that in n equals 0, we actually know that the vacuum state is one of these states. The vacuum state does have a local modular flow. It's just a fact. It's sort of the conformal, the massless theory is conformally invariant. If you take the Rindler result that we talked about and you conformally squish it down to a cone, you get this result, that the vacuum state is KMS with respect to this particular choice of X. So what I'm going to do is I'm going to write down a form for the vacuum endpoint function that is adapted to sort of make this explicit, and then I'm going to start changing X. Okay. So the other fact, which maybe I should call a theorem, this was proved by Stephen Hollins in his thesis, actually, is that there is a very nice form for the vacuum 2-point function in terms of the data on the cone. In fact, maybe I want to write out a big formula. Okay. So if you go and look at Stefan's thesis, you won't see exactly the formula I'm writing here, but you'll see something that is the same up to a change of coordinates. So if you look at the 2-point function in a diamond, and you compute it in the vacuum, and you look at the massless theory, then it has this form. There's going to be an I epsilon. There's going to be a double integral over some coordinate that we'll call eta. And then there will be some funny stuff that I'm going to write down first and explain later. This is the longest formula I'm going to write down in the whole talk, but I'm going to explain why it's kind of natural. Okay. Okay. All you do is you say, well, I had some flow defined on the cone, which in terms of my null coordinate took some particular form. The first thing I do is I choose a new coordinate, eta, which is just the coordinate, the parameter of that transformation. I'm just changing coordinates so that my coordinates are adapted to the transformation I want to study. That's what this means. I choose d by d eta equals x times d by du. That's a u. And that gives me some particular transformation from eta to u, which I'm calling u0 to remind me that this is induced by the vacuum. Okay? And then Stefan just gives us a formula. It's pretty simple, actually. You can see that there's some volume suppression factors, which are related to this u to the d minus 2 that showed up over here. There's some volume factors having to do with the fact that we're integrating over this cone, which has some transverse suppression. There's these E propagators that we talked about before. And then there's just some kernel left over. And the content of the vacuum 2-point function is entirely contained in this kernel, which is just some simple thing in the eta coordinates.
Is it just like that formula, you just plug it in there inside that vacuum and look at the 2-point function on the.
Yes, what I've taken is
Just take
this
one.
1 over sinh squared is the 2-point
Something.
function of this
Right,
combination
exactly.
in the vacuum.
Yeah.
So you have to compute that.
Right.
And then do a change of coordinates and you get this formula.
Right.
The reason this formula is really nice is that I claimed for you that the vacuum was KMS with respect to this transformation. That's actually super obvious from this formula because the transformation, the KMS transformation just does a translation in this eta 1. And if I change this by I and I put that in my sinh squared, that just causes some overall flipping of the factors. You can think that through on your own time. It's pretty simple. It's the sinh just as periodic and imaginary time. Okay. So in fact, maybe I should point out because Nima asked the question, if you look at Stefan's thesis, what you'll see is the 2-point function of this object. And then all I've done to get this formula is transform it into the coordinates adapted to the modular.
Yeah. So by the virtue of exactly what you said, probably this is going to help you with the massive case as well, right? You still are going to have the KMS. You're still going to have something that looks like sinh here.
The massive case, there's also a non-local term. There's corrections to
Yeah.
this that depend on the mass.
Yeah, that makes sense. The math has to or something.
Yeah. Okay, so now that I've told you everything in this form, one of the new results is like totally trivial to state. If I say, oh, sorry. This was a particular choice of 2 pi u 1 minus u. Now, if I pick ux of eta to be adapted to some different vector field, then I can define a new set of correlation functions, which I get just by taking Stefan's formula for the vacuum correlation function and replacing my vacuum adapted change of coordinates by my new one. This is a formula that gives a set of correlators that satisfy the KMS condition for an arbitrarily or mostly arbitrarily specified vector.
The state is Gaussian, so 2-point function suffices.
Yeah, that's right. So we define the state to be Gaussian, so we just specify the 2-point function, and all of the higher point functions are specified by weight contractions. That's right. So let me move from this back to, this will be the very last thing I want to say. 5 minutes or something. Is that in general, there's not going to be any way to take one of these sets of correlation functions and realize it using a real quantum state, something that can be created from the vacuum. So the question we want to ask is, when can we do this? Now, the claim I'm going to present today is that if there is some state in the vacuum sector that realizes these correlation functions, then you're going to need this universal boost-like behavior at the edge of the region. Okay.
That comes from square divisibility.
More or less. It's coming from a powerhouse theorem. And I think maybe the idea will answer what you were just asking. So let me tell you just sort of the idea. We need two things. One, we need an ansatz for what this state would be. Okay, we just need to be able to write down something. We need to be able to write down some ansatz. But the second thing we need is to check that our ansatz is normalizable. We could have written down some ansatz that gave rise to like a fake, non-physical, non-normalizable state. There is a very beautiful theorem in the math literature, the mathematical physics literature, that gives you exactly these two things. And I'm just going to say it very heuristically, there's plenty of, as always, when I'm quoting a math theorem, there are plenty of caveats that one needs to be careful about, but I won't be for this talk. This is what's called the Araki-Yamagami theorem. And it basically tells you what you need in order to get each of these conditions. And the first thing you need is that to even be able to write down an ansatz, you need your X correlation functions to be appropriately bounded in terms of your vacuum correlation functions. If there's going to be a vector in this Hilbert space that reproduces the X correlation functions, they're going to need to have some relationship with the vacuum correlation functions. And this has some funny form, which there needs to be some constant that whenever you take this correlation function, you integrate it against something, you get an upper bound in terms of the vacuum correlation function integrated against the same thing.
Some sort of majorization thingy for the state.
It's majorization for the inner products induced by the 2-point functions. The second thing you need, I'm going to be even more heuristic about. So this one corresponds to even the existence of an ansatz, but then you essentially need to compute the norm of your ansatz and show that it's finite. This is some very annoying mathy thing called the Hilbert-Schmidt criterion. And I'm going to write it so heuristically that no one's even going to know what I mean by it. But basically, it looks like this. What I do is I take these 2-point functions and I treat them as kernels. Right? These 2-point functions get treated as kernels. They get treated as operators. And by treating them as operators, I can start manipulating them as operators. I can take square roots, I can take squares, I can take traces and things like this. This is a very complicated procedure. I haven't told you all the details of it, but it really is. This thing here is exactly the left-hand side of this here. Okay, so I need whatever this complicated thing made up out of these 2-point functions, I need that to be finite. And finally, I will tell you our result, which is that we can show that whenever we violate this universal entanglement behavior, one of these two conditions breaks.
So this is true because it's a free theory or is?
Yeah, this is a statement about free theories and Gaussian states. In general theory, I have like no, I have so little control over the state space that I don't know how to talk about this. So the theorem, something that we've proved, is that if I choose edge behavior for this vector field that is not of the conjectured universal vacuum form, then one of these basic conditions provided by the theorem breaks. If I choose a parametric falloff for my vector field that is slower or faster than a boost, slower or faster than linear, then I end up breaking this fundamental boundedness condition. If I choose my function to fall off linearly, but with a temperature that doesn't match the temperature of the vacuum, I get a breakdown of my normalizability criteria. In either case, what I learn is that within this special class of states where we can really control everything, we can write down sort of this flow generated by the density matrix, we can study whether or not it's actually possible to create quantum field theory states out of the free vacuum that realize this kind of entanglement structure. And we find that we are really restricted, if we want to do this, to look at states that have this conjectured universal vacuum-like entanglement. So for me, I think this is sort of considerable evidence in favor of this proposal that every quantum field theory state or every reasonable quantum field theory state really does have to have some universal vacuum-like entanglement. And then that's telling us something deep about sort of the information structure of the universal ultraviolet divergences of QFT. That's everything. Thanks.
Questions?
Okay. In kind of traditional Gaussian information, like quantum optics and such, there are statements to similar effect that which you presented as 1 and 2, but a little different. There they construct, instead of 2-point, they construct thing known as covariance matrix, which involves coordinates and momenta. So in your case, it'll be 5s and 5 dots, let's say, if we're talking about free field theory.
Yeah.
And there are restrictions of what this covariance matrix might be for it to be an actual covariance matrix of an actual quantum state. Not anything you can write for this will have underlying quantum state, but some of them will, and there are conditions called criteria, whatever. Is this a related kind of project or more relativistic quantum field theory setting as opposed to few modes?
Yeah, I think it's probably using the same basic theorem, but I don't super know about that work. Do you have any references in mind of specific places? Okay, that would be great, because I'm just not familiar with it. But it sounds like it's doing the same thing in the continuum.
Right. Those people who do multi-mode.
Right.
So large, let's say, some number of hues and some number of conjugate moments. So in that sense, it's finite system. Well, yours apparently is not.
Yeah, so I think it's probably essentially, if I were to discretize this, I think I would probably get back the condition that you're talking about. Yeah.
But they use a lot less. They only use phi and phi dots. Again, if I translate it into your language, at the same spatial slice, so to speak.
Yeah, so I could have taken, so this is some covariant thing, but I could have taken this and sort of projected it down to a slice using the equations of motion. And then it would be written in terms of phi and phi dot.
Okay, then it does begin to look kind of close.
Yeah, that sounds pretty similar.
I think this is the most general thing possible. Could write down this for a one-time analogy, for general quantum systems. Both of the conditions, even though you're writing them in this particular way, so single harmonic oscillator, qubit, these are, if you want to check the first two conditions, so you have an ancestor and it's normalizable, you become these two.
Yeah, but I think the core of the question is more about, you know, the relativistic theory lets me turn phis and phi dots into phis using the equations of motion into space-time phis. Yeah. Yeah. But I think, I mean, if I were a non-relativistic kind of person, then maybe I would have written all of this in terms of phis and pi's from the beginning.
I see.
Any other questions?
Yeah, I just have one question, which is, when you said every good quantum field state looks like the vacuum equilibrium. That's intuitively like you zoom in close enough and you stop seeing excitations, right? You stop seeing, you see that overall the predominant model is just no particles at all,
Mhm.
no matter the length scale, basically.
Mhm.
That's the
Yeah.
the
Yeah, that's right.
Okay.
Yeah.
I do have a question. If you try to do this, so this was all for free theories, and the question, the core of the question is that if you stick to CFDs, but you talk interacting CFDs, how much of this is generalized? So let's be specific and talk 2D CFDs. And I would have thought all of these would have analogs in 2D CFDs. Interacting ones move it.
Yeah,
correct?
so I think that might be true. What I can tell you is that while we were working on this, there was this interesting paper written by the group at Perimeter. So it's Jackie Caminiti, Federico Capeccia, Rob Myers, and Luca Ciambelli, where they looked at the opposite implication in 2D CFT. So here I said, let me pick a generic vector field, or maybe let me put it this way. I picked a generic vector field. I gave you a state that represented that vector field as its modular flow. And then I told you that the state was not going to be normalizable if the flow was not boost-like. The paper that I'm describing now by the Perimeter group sort of goes the other way around in 2D CFT. They say, suppose that you pick a vector field that is boost-like, then you can create a modular flow, or you can create a state with that modular flow using Virasoro descendants of the vacuum.
This is-
The opposite direction, the restriction, the necessity of the boost-like behavior is not totally clear to me from their work, but it can probably be put together.
It's constructive. Just
Yeah,
constructive.
it's constructed. You just act with a Virasoro generator on the vacuum, and there's so much conformal symmetry in 2D that you can do a lot with it.
And in higher dimensions, the analog of this will hit the same sort of problem that Cassini and friends did when they talked about the Markov property on the cone. Whether there is some sort of Virasoro or with algebra, the cone. I guess we're probably gonna hit that issue.
Why do you think that would be an issue?
Because you're writing an arbitrary flow on the cone.
Mhm.
That is generated by an infinite dimensional algebra supposedly.
Mhm.
That has been suggested by
Yeah,
Cassini's work,
yeah.
but nobody really, unless there's some Q next that sheds light on.
No, I would say not. Yeah.
Okay. But 2D is complete, right?
2D is very simple.
Any last questions? Not, let's thank John.
Thank you so much.